Hello, today we're going to be talking about the wave equation and finding solutions to the wave equation using separation of variables. So let's get right to it. So the wave equation can be written as UTT is equal to c squared uxx. So in terms of boundary conditions, we're going to talk about a fixed domain here. We're going to go from x from 0 all the way to L. Okay, so we're going to do this all with just abstract parameters. You can put the numbers in later on, but I wanted to get the solution out for you. Okay, all right, and then we're going to hold off on initial conditions. We'll talk about those in a little bit. All right, so let's get going. All right, so just like what we've done in the heat equation and the diffusion equation, in the wave equation, we're going to take u of x comma t and express it as a product of two univariate functions, p of x and q of t, and then we're going to plug it in. So then we're going to get p times q double prime is equal to c squared times q times p double prime. Okay, so then we separate, and we get q double prime over c squared times q is equal to p double prime over p. As you've probably seen in other videos that I've done, that I usually put the PDE constant, okay, in this case c squared, on the time side. And that's just for convenience. It just ends up being easier to solve PDEs if you leave it over there. But if you put it on the other side, everything will work out fine in the end. You just have to do a little bit more juggling at the beginning. Okay, so with that, we know the next step, of course, is to say that if this is everything on the left is a function of time and everything on the right is a function of space, that means that the only thing, if these are truly equal to each other, they must be equal to a constant. So that constant, of course, is going to be our eigenvalues. All right, so we're going to go further and then solve that eigenvalue equation. Oh, sorry, we forgot to talk about boundary conditions. So the boundary conditions, of course, are going to be fixed. So we're going to have u of 0 comma t is equal to 0. And u of L comma t is equal to 0. All right, so this is like a guitar string that's anchored on each end. All right, so what we have here is p double prime is equal to lambda times p with boundary conditions p0 is equal to p of L is equal to 0. Right, this has the classic solution of Pn of x is equal to sine n pi over Lx, comma, lambda n is equal to negative n pi over L quantity squared. And this is for n, it starts at 1, 2, 3, and then goes up to 4, and then on for forever. All right, so it should be a good point to note here that in my class, on the exams, I will give you a sheet, essentially a reference sheet with some of these standard eigenfunction sets, or solution sets. And again, I don't want you to have to do all the work over and over again. These specific solutions show up so often. We should really just have them in our front pocket to pull out whenever we need. So I will let you know when it's totally okay to use these sort of canned solutions, when you can just plug them in where you need. So this is definitely a case where this is typically, when I say that this is the classic eigenfunction problem, again, this is classic. This is actually the first one we did a long time ago when we first learned this. So again, I think this is a good example of just trying to be efficient in our work and use our past results to speed us along on our bigger problem. Okay, so I think now we should go to the next page. We have the eigenfunction. So now, of course, we're going to find Q of t solutions. So here's where this is going to now differ from the heat equation. So the heat equation, so now, of course, this is where we're finally going to diverge. Everything since up to here felt a lot like you're solving the heat equation or the diffusion equation, but now we're going to talk about something different. So we're going to now, we have a Q double prime over C squared over Q, and now we're going to have subscripts of n everywhere, and we're going to have our classic eigenvalue here, which is negative n pi over L quantity squared, and this is for n is equal to 0, or sorry, not 0. It's going to be 1, 2, 3, 4, on up for forever. Okay, so we have Q double prime of n is equal to now C squared negative n pi over L quantity squared is equal to Qn. Okay, so this is a second order differential equation. It has a negative coefficient. Okay. So one thing we can do is actually merge this coefficient together and get something like this. Like that. So, and clearly we're asking ourselves what types of functions, when you take their second derivative, they're proportional to themselves times some constant squared and negative, and the answer, of course, is going to be trigonometric functions. So what we have here is Qn of t has to be C1 times cosine of C times n pi over L. Let's change our constants here. I'm going to actually call this an. And then we're going to have C times n pi over L times x, not x, we'll call it t, okay, plus bn times sine C times n pi over L times t. Okay, so those are the solutions to the time problem. And of course we have solutions for 1, 2, 3, 4, up for forever for all those different n values. All right, so the next step now, of course, is now we have to put together everything. So we have the general solution, u of x comma t is going to be equal to the sum, n starts at 1, goes up to forever, times cosine, actually sine n pi over Lx times a cosine C times n pi over L t plus bn sine of C times n pi over L times t. All right, so there's our solutions. So these are called, what we can really think about now is note that we have now an and bn free parameters. These are, of course, Fourier coefficients. They're Fourier coefficients, but the question you might ask is, why 2? And the answer is, of course, we're talking about a second order time dE. We have a second order time dE. So, of course, when we're talking about initial conditions, when we talk about initial conditions, we need both things. We need initial position of the string and an initial velocity of the string. Okay, so what we can say is that u at x comma 0 is going to be equal to f of x. Again, this is given. And we also need ut of x comma 0 is equal to g of x, also given. Okay. All right, so to get an answer from this then, what we need to do, of course, is set t equal to 0, and we get this. And what we're doing here, and I'll circle this up here, when we're looking at our time equation, we see that the sign, when we put t equals 0 in, the sine term goes away completely. And of course the cosine term goes to just an. So we end up with here a Fourier sine series for f of x. All right, that's really cool. The next step we have to do, of course, is look at ut of x comma t. That's going to be equal to the sum n equals 1 up to forever of sine n pi over Lx. That part doesn't change because, of course, we're taking the derivative with respect to time. And then what we're going to get is a negative an times c n pi over L times sine c n pi over L t plus bn times c n pi times c times n pi over L times cosine of n c n pi over L t. Okay, so now if I evaluate at t equals 0 of the derivative, we know that's going to equal g of x, which is going to equal, now when I put t equals 0 here, we know that goes away. So what we end up with is the following. We get a bn, times c n pi over L times sine n pi over L x. All right, so what's happening here is that when we take, so bn, what they have to equal is basically the Fourier, we have to now, instead of having just the normal Fourier sine series, we're going to have a Fourier sine series. This has to be the Fourier coefficient. For g of x. Okay, so we just have that c times n pi over L that we have to scale all of our Fourier coefficients by in order to get the correct ones. Okay, so I hope that helps explain how to find the solution. At any rate, what we have here is our general solution, and I'll write it again, is u general of x comma t is going to be all these trigonometric functions. Just like that. And now we have double the amount of Fourier coefficients to manage, because we have both an initial position that we have to think about and initial velocity that we need to think about. I do want to talk next about, what we want to talk about are these wave modes. So let's look at them. So what I'd like to look at them, we're going to set now, we'll set the bn's equal to 0 for simplicity. And then what we get is these un of x comma t's that are going to look like this. Sine of n pi over L x times, and we're going to set the an's, we'll set those equal to 1 as well. And again, this is just going to be for simplicity, and we're going to get a cosine of c times n pi over L t. These are these wave mode solutions. So what we can see here is that these are oscillating. These are oscillating waveforms of a string, and we have one for each end. So I thought maybe just a little bit we could probably talk about what these look like. So if I have n equals 1, this is the first wave mode. What we have, of course, is u1 x comma t is equal to the sine of pi over L x times cosine of c pi over L Lt. Let's just have a graph of what this looks like. So we can look at t equals 0. So we're really looking at these sort of snapshot solutions. What we have here is a solution looks like that. Right, and then of course if we go to t is equal to some t is later on, I'll just do this all qualitatively. What's going to happen, of course, is we started initially up there, and now things are going to go down a little bit, like that. A little further on, what's going to happen, of course, is we're going to become almost flat. If we go further, then our wave starts going all the way down. And finally, when we get to what value do we get to? If we get to the condition of L over C, if we get to that specific point, what happens then, of course, is that our cosine function becomes equal to pi. That's going to be equal to -1. What we get is an answer. The wave goes all the way down below like this. Okay, and then we go t greater than L over C. We were down there, and now we're coming back up. And we go further on. We start coming back up. And we keep coming back up. And then we start returning. And then finally, when we get to t equals 2L over C, this now we've returned to the t equals 0 mark. And then we can return and do the cycle over again. Of course, this is a model. This looks, of course, like a vibrating string. It could also look like a jump rope. A jump rope type situation here. And this is what we call the n equals 1 mode. Okay, so it's going to vibrate rather slowly and going to oscillate up and down. So what happens then? What happens for the n equals 2 mode? Let's talk about that one. So it actually oscillates twice as fast, i.e. by t equals L over C, one full cycle completes. Recall that the n equals 1 mode took t equals 2L over C to complete. So, and then what it does is it looks like this. It also has what I call a higher spatial frequency. So this is at t equals 0, and then t for greater than 0. What's going to happen is, here was the original starting position, and the amplitude basically just comes down. So it goes down there, and it goes up on that region. And you go on a little bit further, and then ultimately the amplitude for both will be almost nothing. You go further in time, and now half dips below, and the half that was below starts dipping up, and so on and so forth. Eventually you get fully down and then fully up, and then you've returned. At t equals L over C. Okay, and then you complete the cycle again. So these oscillations, they have different temporal frequencies. Each n, you're adding some multiple higher of oscillation frequency, and also a higher spatial frequency as well. The waves become more and more complex, more and more wiggly along the string. Anyway, I hope that gives you some picture of what these solutions look like. I'll talk more about specific solutions in the next video.